what I'll be covering is I'll be focusing on scaling agentic intelligence from pre-training to RL. Some of you might know my background. I have worked on pre-training at Google for a long time, first author of PaLM, worked on Gemini, and more recently this year I joined a startup where we are focusing on building the best frontier open models for agentic intelligence. The startup is called Reflection. You might have seen a little bit about us in news. And our mission is very much on building frontier open intelligence and making it accessible to all. And our the area we are focusing on is agentic intelligence aspects. So let's start with a little bit of history of LLMs, because I come from pre-training, so you have to bear with me here. One of the key focus areas in LLMs has been scaling. What does scaling mean? As you increase the number of parameters in large language models, or you increase the compute that you devote towards training these models, or you increase the amount of data that goes into these models, what we have seen is that the test loss on these models goes down. And what that translates, it has translated to is better and better performance on downstream tasks. And almost until end of last year, we were basically seeing doubling of performance in almost every single benchmark on the logarithmic curve. So basically, the intelligence measure of the models, if you were to call them by the benchmarks that were being used, was improving substantially on natural language understanding benchmarks and reasoning benchmarks and so on. So this was one of the key factors why the focus of almost all the frontier labs was on continuously scaling up the models, because as the models scaled up, the natural language processing, the tasks around reasoning were constantly improving. The other really exciting aspect of large models was this notion of capabilities that only emerge at larger scales. And one of this really important properties was called as chain of thought. So here is an example that we are showing of a math problem. This is a very old example, perhaps, for some of you, but on the left, it's showing that you're solving a math problem with standard prompting, and on the right, you're solving it with chain of thought prompting, where the model is prompted to break down the complex problem. So it's called think step by step into a series of intermediate reasoning steps, and that makes it easier for it to actually give the correct answer. So when it's prompted on the left with the standard prompt, it actually doesn't give the correct answer. And on the right, when it's prompted with this chain of thought prompting technique, it gives the correct answer. Now, why am I showing you this piece of history? The reason this is really important is that it led to significant performance gains on challenging benchmarks related to math, word problems related to coding, and then it really helped us generalize in the reasoning domain. So if you look at reasoning era, for example, the chain of thought basically paved the way for building reasoning models. And here's a very simple example where the model learns to think before answering. This is taken from one of the Frontier Lab models, where the model is prompted to write a bash script for manipulating a matrix as a string. And what you see is that when the model answers, and this is a snapshot of what is in the model output, the model breaks down the problem into multiple steps so that it can solve that problem. So basically, the model is learning how to think before answering, which is very similar to what I was showing you in the previous slide. Now, from the perspective of measuring intelligence, this starts to become a challenging problem, because if you're just measuring static benchmarks like MMLU or GSM-8K or Big Bench Hard, which was not saturated earlier, but like after chain of thought, it started to basically hit the saturation limits, then you do see significant gains that start to come with these reasoning models. However, is the reasoning correct, or is the reasoning just a proxy for the model to have some thinking space before it outputs the right answer? Those are questions that still continue to be open. Now, to build reasoning models, one of the key aspects that has been at the heart of building really strong reasoning models is this notion of being able to do reinforcement learning with verifiable rewards. So as I told you that in reasoning models, you need to be able to have some form of this chain of thought reasoning. But how do you know whether your output is correct or not? So typically, when you were building chatbots, you would go about building these reward models, which would say human prefers this response over this other response. But to build really strong reasoning models, you have to really rely on reinforcement learning with verifiable reports where you have ground truth verifiers. So this is a simple example for a math problem where you're given an input to solve this problem. And with a calculator, you could verify whether the LM output is correct or not. So with RL with verifiable rewards allows us to not just rely on reward models, but now you can go to ground truth verifiers. And this allows us to now improve the model capabilities in math problems, for example, because we can verify whether the answer is correct or not. In code, for example, because we can check if the model is able to pass model outputs pass the unit tests or not. In logical reasoning, for example, where if you are giving a logical reasoning problem, you have certain set of constraints. So you can now check whether the constraints are going to be met or not. And this is easily scalable across all of these categories of problems. So what this allows you to go back to that notion of reasoning models is that now if we have a lot of these prompts that are math problems, code problems, logical reasoning problems, now you can build general purpose reasoning models, which can then, with this chain of thought reasoning, give you the correct answer. So how do you build reasoning models compared to what we were doing for, say, reinforcement learning with human feedback or chatbots? And why is this important? So the pre-training models, the pre-trained base models are pretty much starting on the left. You take your supervised fine-tuning data. This is very similar to how you would do any kind of reinforcement learning with human feedback. But the change here is that in this new paradigm of reasoning, you're also adding reasoning data. So you are using long chains of thought examples. So you're basically adding examples from these verifiable rewards, which have long chains of thought of how you broke down the problem to solve it. And you get this supervised fine-tuned checkpoint, and then you apply general purpose reasoning, general purpose reinforcement learning on top of that. So the difference between so there are 2 points to note here, which I will highlight in just a second. One is that how do you get these long chains of thought, which help you build these powerful models? And the second one is how do you do general reinforcement learning? So getting the long chains of thought does end up being a secret sauce for most of the labs. The general purpose reinforcement learning pretty much comes down to combining the RLVR paradigm with what we already knew in the reinforcement learning with human feedback paradigm. So the belief in the community is that the reasoning generalizes. So even when you train these models on math and code, you can actually get these models' capabilities to work well. For example, if you're doing a deep research agent, you can actually get the model to think before it does any reasoning about what topic it should go research for you. If it's giving you advice, you will see a whole monologue of what it's thinking before it outputs any actual advice for you. And this does also helps factuality in some ways because it reduces the amount of hallucinations that the model might make. But it is somewhat narrow in the sense that we're really training the models to be experts in certain domains. So they really become experts in STEM domains. And if you look at the benchmarks where these capabilities really shine are domains in which you have this notion of verification available. And the benchmarks that really saw a lot of upswing from this notion of reasoning was GSM-8K, math, human eval, and then like subsequent benchmarks like GPQA, and so on, and same for coding. But what's interesting about these set of benchmarks is that they were all static knowledge benchmarks. So the model was basically storing some knowledge, whether that was reasoning knowledge or factual knowledge, and benchmarks like MLU or HelloSwag would basically elicit that knowledge in terms of like the static knowledge that was already present in the model. Or there were instruction following benchmarks where you basically measure how well does the model do in following instructions. They were still short duration, so there was simply one shot, like you prompt the model and you get an answer. Or there were code generation benchmarks like human eval, MBPP, and in those benchmarks, what you see is that like auto completion works really well, or like few lines of code are easy to generate. And then even the problem solving and reasoning capabilities that we just talked about, because they were starting out with human-like chains of thought, they were still very similar to how humans were solving these problems, and sometimes even wrong. Like, we don't have very good measures of measuring whether those reasoning chains were correct, even if the outcome was correct. Now, how does this change? That's one big question. Like, over this year and over the next few years, what are the key changes that we are starting to see? So this is an example of some real-world applications. And this table that I'm showing you is actually taken from Software Atomic Actions suite. There are 5 tasks. What it's showing you is tasks that are as small as a few seconds to a minute, and then all the way up to 8 hours. And the task durations, so the task durations vary a lot. One simple one is like find a shell script. Another example is like do Wikipedia research. Another example, which is taking a long time, is like you need to do backtesting on CUDA. So they vary a lot, but what is really worth noting about these set of tasks is that they require interaction with the real world. You have to make some hypotheses, you have to take some actions, you have to observe the results, and then you have to update your next steps. So it's not just a single shot result, like you ask a question to a chatbot and it gives you an answer. It does require some amount of interaction in some ways. And it also needs to be grounded in the real world because it needs to actually go interact with the real world. So basically, it does require some amount of dynamic problem solving. And these are this category of benchmarks where we still have a lot of headroom in terms of how we measure intelligence, and we only have a few proxies of being able to measure intelligence along these axes. So if we generalize from here to where we consider we would like to be, so we want to be building autonomous agents, and the true measure of agency here comes from perhaps the time horizon of task completion, like how long will it take for the models to complete the task, and reliability. So this graph is showing you on the y-axis the time it takes for the model to complete the tasks 50% of the time, because the models are not yet very reliable. And on the x-axis is showing you the release date. And what you're roughly seeing, it's a log linear plot. What you're roughly seeing is that for a broad range of tasks, the length of tasks that the models can solve are doubling every 7 months. And in software engineering, it's an even faster slope. So the models are starting to solve longer and longer tasks, even though they're not yet very reliable in doing so. And in software engineering, we are seeing way more progress. So what I was talking about here is that in agentic benchmarks, to the measure of what we have built benchmarks for, we are seeing examples of being able to solve longer and longer tasks, but there's still a lot of headroom in how we measure intelligence, or what tasks categorize as the right set of tasks on which we can say we're truly measuring agency. So this is more of an opinionated slide on like what we believe is the path to agency. So typically, if you would like the models to be autonomous agents, you don't just want them to reason more effectively. You actually want them to be able to solve problems over long horizons with a goal. For example, you might ask the model to refactor a code base and use standard logging. And for that, it would have to construct a plan, call a tool, for example, observe the output, and then it might have to reiterate based on what the output was. So it updates its plan and it repeats itself. And it needs to also learn from the failures that happen in the course of doing so. So for an autonomous agent, being able to construct this plan, this goal, and execute it, take the observations, and then recover from failures starts to be really important. So this notion of planning and multi-step reasoning becomes really important as we move towards autonomous agents, and we don't really have very good benchmarks for that set of capabilities yet. The first place where we have really seen, and several speakers in the panel prior to this particular talk also mentioned, the first place where we have seen success in these particular set of tasks is coding agents, where you probably trained your model on, say, a lot of code repositories and bug reports and so on. So when you actually try to make these models useful, they're really useful if you are using any of the coding assistant tools today. And the reason it's easy to measure and build in coding space is that things are deterministic. Like if you run the same code twice, you probably will get the same answer on the same hardware at the very least. Everything is text-based, so we already have achieved pretty significant performance gains in the text space. So logs, file structure, error logs, everything is text-based, so it makes it easier to process things. And everything is, or several things are verifiable. Not everything is verifiable. So like compilers, unit tests provide pretty good execution feedback, provides pretty good signals. So in this particular area, when you build evals or you build even the RL loop, the reinforcement learning loop, it's easier to make progress in this particular space. And this has allowed us to create agents that can take on like non-trivial software engineering tasks, like solving PRs or creating a new feature for a web app or optimizing an algorithm. So you all have probably played around with a lot of the frontier models or vibe coded in some form on Shape. So basically what we are seeing today is a proliferation of tools that have gone from, say, code completion and unit test creation to now we can help the users understand the code repositories, even like large and complex repositories. It does a reasonable job at it. It can reproduce reported issues by writing a new test case, for example. It can navigate code and understand dependencies. It can even apply fixes across multiple files. And SweBench is one benchmark that has tried to capture some of the mindshare of what it means to solve these kind of multi-step reasoning problems when you're basically solving GitHub issues in some way. Now, the thing to note here is that that's only one slice of problems. There's a lot of other problems where startups have gone out and tried to solve these problems, and they have internal evals that they have to construct every single time when they say something is working as an agent. So this is not yet a standardized eval suite, but a lot of headroom has been captured, a lot of value has been captured just because these things are extremely useful. And what has really enabled a lot of these gains, in coding, is that the ability of the model to reason and plan was easy to hill climb on, at least in coding space, with the set of techniques that I was showing you earlier. And then the other key capability that the models have developed is this notion of tool use. So they can interact with the real world via search tools, via APIs, and that allows them to get some output and then be grounded in the real world. So for the case of code bases, for example, I thought I had another slide, but for the case of code bases, for example, you can use grep or ls or file search of some shape and form, and that allows you to search for the relevant information, reason about which API to use, run code in a code sandbox, and then execute that API call if it's safe enough to use. So basically, it allows you to ground your outputs in real world. Now, let's discuss why is this still a hard problem, or why is this not a solved problem, and why we really need strong benchmarks still in this space. So multi-step reasoning and planning, we're just at the starting space of solving these problems. The model needs to be able to plan for task completion. So it needs to have a goal, an end goal, and it needs to be able to decide which intermediate steps solve for the problem. So if it starts solving the problem and if it makes some missteps during its trajectory, it needs to be able to correct itself. And if it goes around in loops or repeated loops, it needs to be able to maintain some coherence over its trajectory if it's a long horizon task. So just imagine your day-to-day of like, you're supposed to complete a PowerPoint presentation. For example, I was supposed to complete this PowerPoint presentation for this particular talk that required multiple step of tasks and perhaps collecting content from various different places. And all of that then needs to be iterated upon. And for a model to be able to do that, and if there was a particular thing that was not amenable to what should be the right content, then it needed to fix that aspect. So imagine that process for an LLM. This goal-oriented thinking, this ability to reason over the entire context window, and the coherence over long horizons starts to become really hard. And being able to break down the benchmarks along all of these axes and not just like end-to-end tasks starts to be really important. So just to double click on that aspect, one of the key challenges as we build large language models has always been this notion of context window. And in multi-step reasoning tasks, we really do see that you end up collecting a lot of retrieved, you end up collecting massive amounts of information in your context if you go, say, 50 steps or 100 steps or something like that. So you do have to manage that context window. And even if you have long context retrieval, say up to 1 million tokens, a lot of the evals will show you very good retrieval capabilities. But if you're trying to reason over that context length, that doesn't quite work out that well. So what that roughly means is that for agentic benchmarks to succeed, or for agents to do well, they need to be able to either manage their context window or reason over the context window that they collect as they make progress in their trajectory. The other key capability that agentic intelligence needs is this notion of task coherence, so that the agent can stay on track as it goes about solving the task. So let's say it's solving a high-level task. In this particular case, this is an example from Terminal Bench, and so it needs to be able to have short-term setbacks and still, over the longer duration, correct course. So the context lengths might end up being bigger than 100K in that particular case. There might be logs that are much longer. So it still needs to be able to find paths and there might be many paths towards like getting to the same outcome. So for the model to achieve these high-level goals, this notion of like keeping coherence over long trajectories is still not easy to quantify, and a lot of the work that researchers end up doing is basically measuring it on a per step level today. So to summarize what I've been saying for the last few minutes here is the key points here is that long horizon tasks still continue to be extremely challenging because you have to really reason over long form reasoning chains. You are going over multiple steps, and that problem is not solved. Even with SweetBench, you don't really quantify all the nuances of that problem. You have to solve this notion of credit assignment over, say, thousands of steps if you're taking thousands of steps. So that problem is still an open problem, which is definitely something we try to solve. You need, if you're doing any form of reinforcement learning, you need some form of, like, say, golden trajectories, depending on the task that you're choosing. And you really need robust verifiers. How do you verify that every single step was correct, or is it enough to have just the final outcome be correct? Those are still open questions in this particular space. And then finally, if you are building reinforcement learning loops, which is the kind of work we are focusing on, you do need like synthetic environments to act as gyms for these agents to build upon. And this really touches upon this nuance of this idea, because we focus a lot on reinforcement learning, where to train these kind of agentic systems, it's not just like we need really strong evals in this space. We also need really strong environments, rich and interactive environments, where the model can learn from experience. So this is where the environments can act as, say, synthetic data, for example. So you can have simulated code repositories, or you can have simulated any kind of environment which can practically give you a lot of data for the agent to manipulate certain set of states, have access to a certain set of tools, and then in terms of tasks, basically the agent is given a set of tasks to go attempt, and then how to solve those tasks correctly needs to be well specified, and there needs to be some form of verification loop that allows the agent to know whether what it was doing in that environment was correct or not. So this basically gives you almost unlimited data if you were doing it in just the right shape and forms for all the tasks that we might care about across the board. And this kind of opens the door for, like, if you could scale across a lot of diverse tasks and challenging tasks, for example, that require advanced reasoning, tool use, and longer time horizon, you basically have a path to perhaps a general purpose agent here. At the same time, a lot of these things are not easy to measure. So building that closed loop of what would scale well is still a lot of open problems in that particular space. And this is where, like, being able to measure agentic intelligence becomes a hard problem. And this is a nuanced take on the fact that it's not just at the post-training level that you need these models to improve. Even at a more basic level, for these models to work well as general purpose agents. So there's the multi-step reasoning and planning we talked about. There's the tool use we talked about. But the long-form reasoning and self-correction are capabilities that perhaps the model more fundamentally needs to be able to reason about. And those are capabilities that perhaps the language model can learn much earlier when it's being trained. And then the other big aspect is that what is the diversity and the ability to adapt to dynamic environments. That's another aspect that is really important for building general purpose agents. So if we go back to the vision of what we believe will lead to autonomous agents, we believe that for a strong proxy for agency, it really comes with when the model can solve longer time horizon tasks and can do so reliably. And even though we see that models can complete approximately 50% of the time, that length of tasks is doubling every 7 months. The reliability component is still largely unaddressed, and then that aspect of measuring intelligence doesn't have very good benchmarks either. So with that, I would basically say that I think there's a lot of open questions in this space, both in terms of building really strong agentic models and measuring intelligence while we are building them. And how do you do that? It continues to be a challenging and fun problem. With that, I do want to make a call out for hiring on our front. So at Reflection, we are building these frontier open agentic models that we want to make accessible to all, and that hopefully will provide a platform for building better benchmarks, eval benchmarks on top of that. And we believe that open models are critical both for building better benchmarks and for folks to build commercially on top of them. So if this is something that you find really exciting, we are over 60 researchers and engineers from top labs across the board. So we would love for you to come join us, and you can either DM me on Twitter or email me afterwards, or come find me right after the talk.